Project Pulse, Reawakening the Red Planet. I'll never forget the day our ambitious plan to restart Mars's core was given the green light. After years of simulations, calculations, and skepticism from more than a few naysayers, the international science community had finally approved our highly unconventional proposal. Project Pulse was a go. The idea first took shape during a seemingly innocuous conversation over beers at Howard University's faculty club between myself, Dr. Peter Jafari, the geophysicist, and Dr. Caterina Velasquez from the Aerospace Engineering Department. Do you guys ever wonder if we could do something to give Mars its magnetic field back? I asked them, somewhat absent-mindedly. It's kind of a shame such a potentially habitable world lost its planetary dynamo billions of years ago. I'll never forget the excited glint in Peter's eye after I nonchalantly tossed out that musing. He launched into an enthusiastic tangent about the geological and atmospheric ramifications of Mars losing its global magnetic field, from stripped atmospheric gases to increased radiation bombardment on the surface. If we could somehow restart that sucker and get the iron core churning again, he kept repeating, deep in thought. From there, the wheels started turning, and before long, Katerina and I found ourselves sucked into Peter's ramblings about using gigantic magnetic field generators to attempt to reactivate Mars's core through controlled electromagnetism. Hear me out, guys. What if we constructed two massive orbital magnetic field stations that essentially formed an electromagnetic bottle around the red planet? If we generate powerful enough magnetic fields and oscillate them in just the right way, well, in theory, we could induce current flows in the iron core and potentially kickstart the dynamo reactivation process. His idea was ridiculously ambitious and borderline science fiction. But the more we discussed the potential methods and required engineering scales, the more I found myself convinced it could actually work. Fast forward 7 years, and here I was standing in the temperate biodome of Longway Base, one of the first permanently inhabited human settlements on Mars, staring out across the rusting sands of Prometheus Terra in awe of the two gleaming orbital stations slowly taking shape. Pulse 1 and Pulse 2 were the most expensive, ambitious megastructures ever constructed by human civilization. Each station consisted of a gargantuan 32-kilometer-wide ring of hyper-condensed magnetic coils capable of generating localized magnetic field strengths over 1 million times that of the Earth. Just the logistical challenges of transporting that much construction material from Luna and reassembling the electromagnetic arrays in Martian orbit had been an engineering nightmare. Constructing the stations using next-gen robotic swarms took 5 years of complex choreography executed with surgical precision. But looking at them now, suspended in the rust-tinged sky, they were an astonishing sight to behold. Our calculations showed that if we could initiate a complex interplay of opposing magnetic field pulses between the two stations, focused inward on the red planet's core region, we might just be able to induce enough current flow within Mars's iron-nickel interior to restore the heat convection processes that once powered the red planet's global magnetic dynamo. The hope was that by stirring those internal currents, it would actually end up liquefying Mars's solid core over an extended period of intense electromagnetic battery. Eventually, the molten iron could churn in the ways required to regenerate a long-lasting, sustainable internal dynamo, recreating a protective magnetosphere around Mars. At least that was the extremely ambitious theory we were about to put to the test. For such an audacious concept, Project Pulse had begun with incredibly humble origins as one team of scientists batting around reckless ideas over drinks. But after running the numbers and modeling the possibilities with the university's computational physics labs, our proposal quickly gained mainstream traction and was ultimately greenlit for real-world implementation on Mars as part of the International Colony Initiative. And now, here on the eve of our first full-powered magnetic field induction sequence, I could feel the same mix of nervous excitement and optimism that first gripped me all those years ago in the campus pub when this crazy notion was born. After performing a final round of systems checks and coordinating protocols with each station's science teams, we were finally ready to ignite the twin magnetic field generators for our first true trial by fire. Taking a deep breath to steady my nerves, I toggled the intercom and announced, "All stations, field generators are primed and ready. We'll be initiating the ionization sequence in T-minus 5 minutes. Begin shutdown of all electrical systems within a 2,000-kilometer radius and batten down for potential electromagnetic fluctuations. Anyone unshielded within 2,000 clicks of the pulse arrays was risking severe electrical burns, radiation damage, or worse from the intensity of the magnetic fields we were about to generate. Over the past 2 months, all sensitive electronics, spacecraft, vehicles, and electromagnetic systems had already been turned off or shut down around the primary blast radius. After verifying all other teams were ready and final safety procedures completed, I relayed the firing command. Pulse 1, Pulse 2, initiate startup sequence in 3, 2, 1, mark. No matter how many simulations I had sat through, nothing could have prepared me for the sheer visceral force of those magnetic field generators firing up in synchronized succession. Even from over 160 kilometers away, our heavily shielded base briefly flickered as an ominous subsonic rumble rippled across the Martian plains. Within seconds, the massive superconductor rings began glowing with eerie, invisible magnetic ion clouds as their colossal field envelopes expanded outwards from the aerial stations like slowly inflating force bubbles. Soon, the two radiant tori had encapsulated the red planet in intersecting planes of seething electromagnetic containment fields. At that moment, Mars's upper atmosphere became visibly distorted and destabilized, with waves of atmospheric ions rippling and warping before our eyes. The sheer magnitude of the artificially induced magnetic influence being impressed upon this entire world was beyond description. Our power readouts soon confirmed field strengths rapidly reaching over 10 million Teslas focused on the core, a new record only made possible by the advent of graphene-based metamaterials. With the station fields primed in oppositely phased magnetic alignments per our intricate calculations, it was time to fire the primary pulse induction sequences to trigger the core dynamo. I took one last look around at the teams of engineers, geologists, and technicians assembled throughout Longway Base, a truly international coalition representing nearly every nation on Earth. All right, people, let's make history. Initiating core resonance pulse on my mark. 3, 2, 1, mark. In split-second unison, the pulse stations unleashed their carefully choreographed barrages of magnetic field oscillations aimed inward toward the red planet's core region. Huge arcs of magnetic shear appeared to twist, warp, and pulse across Mars's upper atmosphere like some sort of cosmic tsunami as the arrays pumped terawatts upon terawatts of electromagnetic induction into the iron-rich interior. For the first few minutes of the initiation phase, nothing visibly momentous occurred beyond the atmospheric distortion patterns and a few stray electrostatic bursts flickering across the plains. The only indications our plan was even working came from the seismic and gravimetric data flooding into our monitoring stations. Our magnetic oscillations were most definitely perturbing and destabilizing the internal iron flows within Mars's outermost core boundary. But then, just after 27 minutes of continuous pulsed induction, something rather shocking began occurring across the red-tinted horizon. At first, it looked like some kind of faint, localized atmospheric glow, akin to visible oxygen ionization trails in the upper atmosphere during an auroral event. Except these gossamer streamers of energized particles appeared to originate below the surface, near the core region itself. "Doctor, I think you'll want to come take a look at this," one of my geologists called out, voice dripping with awe. He didn't need to ask me twice. Over the next hour, we all stood transfixed as the spectacle in the distance gradually escalated into one of the most mesmerizing displays of electromagnetic pyrotechnics any of us had ever witnessed. Swirls and vortices of ionized matter began erupting outward from localized hotspots along the planet's northern and southern hemispheres, spiraling outward like cosmic double helix sculptures made of neon fire and lightning. It took us several minutes to realize we were actually bearing witness to the magnetic induction process, successfully jump-starting the churning flow of Mars's previously dormant iron core. Our focused bombardment of powerful electromagnetic influences had effectively transformed the previously inert interior into a violently sloshing, molten sea of superheated heavy metals, iron and nickel. As the liquid dynamo currents accelerated and grew in strength, so too did the scale of the magnetic plume phenomena we observed on the surface. What had begun as a few isolated atmospheric glows soon transformed into raging storms of charged particle radiation bleeding through transient magnetic rifts across the rust-tinted horizon. Thanks to our station's carefully modulated oscillation sequences, we were essentially jump-starting and guiding the magnetic regeneration in a controlled directional flow, mimicking the natural process of a planetary dynamo, but on an exponentially accelerated timescale. It was like EM kickstarting a car engine, if said engine was the size of Mars itself. The spectacle grew increasingly cataclysmic over those first 12 hours as Mars' rebirthed core dynamo gained strength. Blinding auroral coronas swept across the shimmering skies while rivers of incandescent plasma vented from fracture networks unseen on the planet for billions of years. At times, the overwhelming pyrotechnic forces caused localized electromagnetic pulses that tripped breakers and disrupted systems back at our base. After nearly a full day of continuous magnetic induction, our sensor arrays began detecting definitive proof our efforts were working. Mars had finally achieved something it hadn't possessed for over 4 billion years, an intrinsically generated global magnetic field. Where there was once virtually nothing to stem the endless onslaught of cosmic radiation upon the surface from solar winds and interstellar particles, the red planet now glowed with a newly reconstituted magnetosphere. A ghostly aura of looped force lines reminiscent of Earth's own natural magnetic cocoon against the void, but far more diminutive in scale, at least for the time being. Over the following weeks and months, as the pulse arrays continued their magnetic manipulations, coaxing and strengthening the core flows, Mars's inner dynamo effect grew increasingly more pronounced. Eventually, the raging atmospheric phenomena settled down as the churning iron ocean below smoothed out into a consistent rotational flow pattern. Soon, we were seeing detailed magnetopause models revealing multiple well-defined regions of magnetic sphere influence, interior field lines looping across the solid surface from pole to pole, while exterior lines stretched out into the cosmos like a hard-won force field bubble reclaimed from the harsh environment. While nowhere near as robust as Earth's magnetosphere, this nascent magnetic field proved more than adequate to begin shielding the surface and what remained of Mars's fragile atmosphere from the ravages of cosmic radiation. If properly maintained and built up over time, there was hope Mars may regain the atmospheric density required to finally become a long-term thriving human habitat. Just as we had theorized, overcoming the initial core solidification inertia proved to be the most difficult step in the process. Once molten metal flows were established, the inherent rotational momentum and heat convection did most of the heavy lifting in terms of perpetuating a self-sustaining magnetic dynamo effect. Our station's arrays simply entered periodic trimming mode to keep the fields calibrated and strong. For myself and the Pulse team, witnessing our wildly ambitious undertaking come to life was the greatest reward of all. What began as drunken theorizing between colleagues over beers in the campus pub had ultimately blossomed into one of the most historic milestones of off-world engineering. We had quite literally reshaped and rejuvenated an entire planet's intrinsic core dynamics from scratch, the first humans to have accomplished such a feat. And in doing so, we took Mars one vital step closer to becoming a viable new home for our species among the stars. While the red planet's newly re-established magnetosphere represented a seismic shift in its environmental prospects, the work was far from over. Over the coming decades, as that magnetic shielding effect allowed Mars's atmosphere to slowly replenish, generations of scientists and colonists would turn their focus to larger-scale terraforming ambitions like atmospheric manufacturing, water reclamation, forest seeding, and full biosphere reconstruction. But in that triumphant moment of watching Mars reclaim its protective magnetic force field for the first time in eons, I couldn't help but smile with the realization that my fellow human beings had achieved something once thought to be reserved only for the gods.